I want to look at a few more examples of series that you need to recognize. So let's say that I was asked to write the first few terms of a series representation centered at 0. So this is technically a Maclaurin series. For the function f of x equals 1 over 1 plus x cubed. Okay? You are not expected to try to take a bunch of derivatives and match things up for this. This should be a form that's relatively familiar to you. Okay? Now, it may not be super familiar to you on this date because we haven't talked about it for a while. But if you remember, when we first started talking about series, I showed you just a really basic series. I showed you the series 1 plus x squared plus x cubed, and so on. And this is just a geometric series. You're multiplying each term by x to get the next term. And so we'll say that this series would converge if the absolute value of x is less than 1. In other words, if x was a half, for example, 1 plus a half plus a fourth plus an eighth plus a 16th and so on would converge. Anyway, if you remember, the sum of an infinite geometric series, if it's convergent, the sum of infinitely many terms is equal to the first term divided by 1 minus the common ratio. Okay? If you think about how that pertains to this, the first term here is 1, and the common ratio is x. Okay? And this is my functional representation, or the function that is being represented by this series. Okay? And again, it's being centered at 0. Anyway, if we substitute values near 0, specifically between -1 and 1, this series will approximate this function right here, okay? And again, if I wanted to do a function that was similar, like if I wanted f of x equals 4 over 1 minus x, that's just 4 times this series up here. That would be 4 plus 4x plus 4x squared plus 4x cubed, and so on, okay? Remember that x is your input, okay? So the way that I read this a lot of times is I'll say if I have 1 plus x squared plus x cubed and so on, and it's representing the function f of x equals 1 over 1 minus x, I'll say that this is representing 1 over 1 minus the input, okay? And so this is 1 plus the input squared plus the input cubed and so on, which means if I had a function that looked kind of like this but was tweaked slightly, so it could be multiplied by something, you could add or subtract a value to it, and that might knock, like if I had this function minus x, you could just knock out the x there and the rest of the series would be what it is. If it was that function minus 1, you could just knock out the 1 and start it at x and go from there. If it was 1 over 1 minus x squared, okay, notice x was the input. And you got x, and then x was being squared, and x was being cubed, and so on. Now your input has changed to x squared, so you're going to have 1 plus the input to the first power, plus the input to the second power, plus the input to the third. So we're going to have 1 plus x squared plus x to the fourth plus x to the sixth, and so on, okay? If I had 1 plus x, if I had something like that, okay, again, you would look at that, you would say, well, that looks kind of like 1 over 1 minus the input, except it's 1 plus an input. Can you write it into the form 1 over 1 minus the input? And the answer is yeah, sure, I can write it as 1 minus negative x. That's the same thing, right? And so I've changed my input to negative x. So then this series is going to be 1 plus the input, input's negative x, plus the input squared, plus the input cubed, and so on. And so it'd be 1 minus x plus x squared minus x cubed. It would be an alternating series, okay? Just flipping that sign there does that, okay? So going back to the one that they gave us, a couple things need to happen here. You want to write it as, so it looks a lot like the kind of thing we've been working with. You want to write it as 1 over 1 minus some input. Okay, well, how do you do that? You write that as 1 over 1 minus negative x cubed. okay? So instead of 1 over 1 minus x, it's 1 over 1 minus negative x cubed. And you just have a negative x cubed as your input in each of those positions, okay? So I would have 1 plus negative x cubed to the first, plus negative x cubed to the second, plus negative x cubed to the third, and so you'd end up with 1 minus x cubed plus x to the sixth minus x to the ninth, and so on. And you can kind of figure out what your pattern is from there. So you can tweak these things, okay? Now there's one other thing that you can also do, and this can be kind of tricky for people. So you can also represent f of x equals the inverse tangent of x as a series centered at 0. And on the surface, you look at that and you go, what? That doesn't make any sense. What does that have to do with anything we've been discussing? But the derivative of the function, the derivative of the inverse tangent is 1 over 1 plus x squared. And I can write a series representation of the derivative of the function, okay? F prime, so you look at this and you say, boy, that looks a whole lot like the infinite series sum, the infinite geometric series sum. Oh, it should be 1 over 1 minus the input. So I'll write that as minus negative x squared, okay? So it's going to be 1 plus the input to the first power, plus the input to the second power, plus the input to the third power, and so on, okay? I'm going to simplify this here. I've got a reason. That's going to be 1 minus x squared plus x to the fourth minus x to the sixth, and so on, okay? Now you're looking at that, you're saying, wait a second, that's not the function we were supposed to represent. That's this. That's the derivative. I want to represent this. Well, one of the reasons that we want to be able to write non-polynomial functions in polynomial form is that it's really easy to take derivatives and integrals of polynomial functions. So I can take the antiderivative here. If this is the derivative, f of x would be x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, okay? I can just represent it that way. So you can take derivatives and you can take integrals. So watch out. They may ask you to find a series representation for f prime, or they may have something where they give you f prime and they ask you to write a series representation for f, and you have to take the antiderivative. These kinds of things will happen. So it's a pretty famous trick here, okay, kind of a special case, but again, it's a pretty common use of using the geometric series idea to represent functions as infinite series. So be on the lookout for things that look like the form 1 over 1 minus x. If so, it's probably a tweaked version of a geometric series, and you should be able to make some kind of connection to it.